Hi guys, 6:30. So we're going to continue with the second half of today lecture. Just a quick recap. So we're using fastai and we're using the MNIST data set, right? And we're trying to do image classification, basically. So currently, we opened the MNIST data set from fastai. We just used the 3s and 7s, so basically like a 2-class problem, right? Not the 10-class problem that usually MNIST will have. So currently, we're trying to build a image classifier, and we're just kind of playing with images and showing you some things that you can do. We'll finish this discussion with how to implement a classifier with fastai for MNIST. So we'll do that. But right now, you guys are helping me to just build a classifier by just averaging images and taking distance metrics. So remember that a lot of machine learning and deep learning, deeply, if you think about it, it's about these vector spaces, right? Whether it's called an embedding or whatever it is, there's always these ideas of how to create vector spaces, and then you have distance metrics. So here, just to recap, we took all the 7s, all the images of 7s and all the images of 3s in the MNIST data set, the training set, and we stacked them basically as tensors of 6,131, 28, and 28. We grab these from the train set. We will repeat this task shortly for the validation set or the test set, right? And this is so that we can measure performance later on as we go towards building this in fastai. But right now, I'm just trying to build a classifier based on the mean of the images, and just think about how we could do something like that. All right, so we have I think we run this. I showed you the means of the 3s and the 7s, and then we just grabbed an image like a 3 basically, and we calculated the distance between that 3 and the average of all 3s and the average of all 7s. We use two metrics here basically. These are referred to as L1 norm distance and L2 norm RMSE. But basically, the one has squared and the other one is absolute value. We take the distance between A3 and the mean 3s, right? Using both equations, and we get these values here, 0.11 and 0.20. Then we repeat the exercise again and compare A3, that 3 image here, effectively, to the average of all 7s, which is this one. And as you can see, it should be more different, right? There are more differences. So then here, basically we get an error, so we can compare them. So we can compare 0.11 to 0.15, right? And we can compare 0.20 to 0.30. So basically, you can think of this as a similarity. 0.20 means that it's more similar than 0.30, basically. Okay, so I think that, yeah, that's where we left off. So now we're just going to keep going, trying to build this as a classifier. So that's basically this and that part. All right, obviously I built I've used like kind of the equation approach. As you know, PyTorch provides functions that we can use for this. Right, the L1 and L2 are in Torch. All we have to do is import Torch NN functional as F or Torch F, or we can use or fastai already has its own way of calling them as well, right? So there's a lot of wrappers and abstraction basically. So in this case, I'm calling F1.L1 loss and F.MSE loss, right? Basically, it should give us the same values, right, as before. I'm going to compare A3 to mean 7 and A3 to mean 7. All right, so let's run that. All right, so we got 0.15 and 0.30, 0.15 and 0.30, effectively the same result. Okay, so now we have a metric. We know that we have the average of 3s, the average of 7s, and we can compare all of our samples to that. Okay, this is basically what algorithm in machine learning? KNN, right? This type of a KNN always comes back to KNN, right? As an intuitive thing. All right, so now let's go ahead and just look at a few more things. a few more tools. So I'm going to take here's an example of some data. So this is just a list, right, in Python, and we're going to invoke FastAI's array and tensor functions. So this is FastAI's way of incorporating NumPy, FastAI's way of incorporating Torch. Again, it's just, you can mix up FastAI, Torch, etc. All right, so here we can run this, and you can see we take the data, convert it into an array. It's effectively a NumPy array. If we run the data and run it through the tensor function, it should become a Torch tensor. Okay, you can actually print out the data types. Okay, so this should say NumPy and Torch, right? So we're going to go ahead and run that. You can see one is now converted into a NumPy array, one is converted into a Torch tensor. So you can see that it's the underlying libraries in the background, but just wrapped around with FastAI code. All right, so we keep going, building this application. We're going to look at a few other things that we can do, like slicing, before we get to it. So here, TNS is this one, right? So let's go ahead and take a look at that. I'm going to run these individually so they don't become confusing. All right, so I'm going to run this one first, right? And it gives me basically the first row of the original data. Then we can slice. Okay, all the rows in one column, right? There you go. So yeah, so all the rows of column 1 to 5, right? Okay. So same things as before. Can do this one. What is this one? Row 1? No. What is it? 0, 1, and columns 1, 2, 3, right? So it's 1, 2, yeah. So 5, 6. 5, 6. So it's row 1 and those last 2 columns. Yeah, very good. TNS1. So everything got added the value 1. Yeah, so 2, 3, 4, and so on. You can see that, and so on, right? So you can run these on your own. All right, so just basically looking at some operations. Okay. All right, so now we're going to build kind of the validation set, okay, just like we did the train set. And this is, as I said, because we are going to build a FastAI approach to this at the end. Oops, sorry. Be this one. All right, so this is the validation set, create Torch tensor and normalize it for 3s and 7s. Notice that here now we are grabbing things from validation instead of train, but it's basically what we did before, right? We iterate through all the 3s, all the 7s. We use pill image. This is a list comprehension, and we convert it into a tensor basically. So we have effectively a list of tensors, and now we stack them with Torch. So this is the validation set for 3s and the validation set for 7s. What are we doing here? We're just converting to float and normalize. Everyone with me? Pretty straightforward, right? So if we print out the shapes, we should see, this might take a while. Yeah, that it's similar to the other one, but this is smaller, right? I think the other one had like 6,000 samples. This has 1,010, 28 by 20. So it's the test set. All right, and we'll use this. Just we'll keep it there, but we'll use it to evaluate our model. All right, so now, as I said, we're continuing with this idea of just building a very basic classifier just by distance metrics. So let's create some kind of a distance function. Okay. So this is a function to get the mean absolute error with the tensors, right? A minus B. This uses broadcasting, which is a thing in when you're doing these kinds of operations. The -1 and -2 tells Torch to calculate the mean only on the last 2 or 3 axes, i.e. the 28 by 28 part, okay? So remember here we have number of samples, right? So we have number of sample 3 and then 28 by 28. Sample 7, 28 by 28. So the mean, we should for all 1,000 images, right, we calculate the mean. Okay, so we're going to end up with something that is of size 1,000. And we'll see that in a second. So our goal is to take the difference first, then do the other operations. So this mean MNIST distance takes A and B, right? So this could be one image and the average, or it could be a stack of images and the average. And that's where the broadcasting comes in. That's a thing in Python that's available. And it's very powerful with tensors. Okay, so that's this function here. So we can test this out. So here I'm just going to take my original A3 and the mean 3. Right? Everyone with me? Okay, all right, perfect. As I said, I'm just kind of going through this idea of KNN and kind of playing with images. All right, 0.1114. I'm pretty sure we had seen this before. All right, so let's keep going. All right. Take a look at this one now. So what are we doing here? Now we want to calculate a metric for overall accuracy of a batch of images from the validation set. So, and we want to do all 1,010 at once, right? So we want to do that batch of images. So we can, our function that we wrote here works because of broadcasting nicely for all images as well. All right, so I'm going to do that here. Notice MNIST distance. It'll take now the mean 3 still. Remember, this is still just one image, 28 by 28. That's the average. But here, this should be what? This should be 1,010 by 28 by 28, correct? All right, so we're going to take that distance of all because it's going to broadcast it, and it's going to give us the distances. Pretty quick, right? So now let's go ahead and do that. So I'm going to print val 3dist and also the shape, which is really important here. All right, and there we go. We have 1,010 because we have 1,010 distances. For each image in our test set or validation set, we've compared it to the mean 3 image, and we've got the distances, which are basically these values here. Any questions?
What's the shape of it?
What is the shape of mean 3? It should be 28 by 28.
So valid mean table is 1, 0, 1, 0, like 8, and the shape of mean 3 is just 28 by 28.
Yes. Or 1 by 28 by 28. So what? Broadcasting. That's the answer. So do you know what broadcasting is? So broadcasting is this trick in Python where sometimes broadcasting basically in this case would be you have 1,010, 28, 28, and 1, 28, 28. When you have an operation like that, Python will sometimes make intelligent guesses if the dimensions align. So effectively what it's doing is it's taking that 28 by 28 mean 3 and just copying it so that you have 1,010, right, entries that are 28 by 28, but here you just provided one that was 28 by 28. But Python understands, these have similar shapes, so I can just copy this and apply the operation to all. And that's called broadcast. It's like you have to kind of read in. It doesn't always work, and you have to be very careful. But if you do it right, you can do operations such as this one. And that's kind of what, you know, for me to go into broadcasting, I'd have to do a set of exercises and give you I don't have, it's like there's a set of rules. Like for broadcasting to work, these like, let's say 7 things need to be true, and then it'll work. But I can print the shape, so we can definitely do that. So let's let's do it here. Let's add a cell. So valid three tens, right? So that goes in. So I'm gonna do here dot shape. You see that's 1010, 28 by 28. This was invented almost because this is what we do in machine learning all the time, right? We're like comparing a whole bunch of things to an average thing and calculating the distance. So it makes sense to do it. Now let's take a look at mean 3. (28 by 28). You see that? But when we are performing this here in the equation, right? So you can see that. And so this A and B is not the rest. Don't be confused with this, right? This happens after. But this part here, the A and B, is basically where it takes the 1010, 28, 28 minus the 28, 28. But because they kind of align, it'll perform a broadcasting operation. And a good way of thinking about it is we have these 3 items. You're going to compare to this one. It'll just copy it so that you can perform the operation, as long as the dimensions match up. Got it? Does that make sense for everyone? All right. Okay, great. All right, so we did broadcasting basically. And then once we do broadcasting, this mean thingy here happens so that you can average out the errors, as you call them, the differences between the pixels. Okay, so let's go ahead and run this one. So you can see there, I have 1010 differences or distances, and I just printed the shape. Okay, so effectively, this is a type of a classifier, right? Because I can compare this to the 3s, or I can compare these to the 7s, and then know, based on the distance, what it's more like, what's this, more similar to. Okay, so let's keep going. All right, so we did this part. Now we can try to, this is not the greatest function, but we can think of how to create a function here. Maybe you guys have a better idea. But let's say, just like we did, is cat here, because this is a 2-class problem, right? We only selected 3s and 7s. So you can generate a is3 function, right? And so you can see what it does is basically it performs the mness distance twice. You give it the x and it compares this to the mean 3, or you give it the x and it compares it to the mean 7. Do you see that? And then it compares, obviously it's a distance, so it's comparing which one is bigger, right? And if it's 3, this one should be lower, right, than this one. And the condition should be true. Otherwise, the condition should be false. And that's basically your classifier right there. Got it? All right, great. So let's run this function. Let's add it in there. Okay. So raise your hand if you have any questions. Okay, so now let's go ahead and basically evaluate this. Okay, so let's go ahead and do that. So we're in a print A3. Is it a 3? Right? And then we're also going to take the whole validation, the whole stack, right? And compare all of those. Let's take a look. So you can see that basically what it does is it returns, it's a Boolean condition, so it returns either true or false. So it's saying here it is a 3 just because of this condition that this value is less than this value. It finds that to be true. In some cases, it doesn't find that to be true, and it will give you a false. Got it? If you want to convert it to float, that just means you convert it to a number, basically, 0 or 1. Any questions? All right, let's keep going. Add a few more cells. Now we want to try to calculate accuracy on this model. So you guys can help me out here. Okay, so calculate accuracy on this model. Is 3, basically that's the accuracy for the 3s, but we also have to evaluate the accuracy for the 7s, right? When we give it the 7s. And we do this 1 minus for the value. So let's go ahead and do that. Okay, and so here we add the accuracies of 3s and the accuracies of 7s divided by 2, and this would be for the 3s, for the 7s, and the overall, basically. Any questions? No questions? All right, great. So yeah, so as I said, we don't usually do these functions by ourselves, but this is just kind of playing with this is based on the trues and the false, right? So it's basically evaluating that. We're taking the mean of them. So how many ones, right? So there's a few. So we add up the ones and divide it by the total number of them, and that gives us the percentage, basically. All right. All right, so that concludes that, which is basically trying to do just to play with images and trying to build a classifier comparing to the means. Okay. The next, I have 2 more things for today that I'm going to do, which is building this same MNIST with fastai. But first, I'm going to try to give you an example of a question that you guys had last week. All right, which you were asking about the weights of the, how are they updated and all that in the classifier. So we're going to take a look at an example of this. I was playing with this. All right, so let's take a look. So we're going to assume the loss function of MSE, okay? So basically we have 2 loss functions in machine learning and deep learning, which are what? MSE for regression and then cross entropy, right? Cross entropy is a little bit more complex, so we're going to do this with MSE basically. And we're just going to try to visualize a little bit what the weights look like, what the gradients look like, and all that. All right, so let's take a look at that. All right, so basically, this is some of the underlying concepts in the training process and stochastic gradient descent. So obviously in the previous technique that I tried, we did not learn weights from a model, right? So we weren't learning weights. So now we can look at gradient descent so we can learn some weights. So this should motivate this idea of the stochastic gradient descent. And we're going to do this on this quadratic equation, right? So let's kind of start with that. So we're going to lay down some things, some ideas. So I'm going to call this example, super simple example of the weights, the weight of calculating weights. Example of calculating the weights. Okay. So we need to define a few things. So in machine learning, there are 2 functions, okay? The inference function and the loss function. Almost think of them, this may not be true, but think of them as rivals. They're, playing against each other, all right? This is going to be the loss function, okay? Which is actually very close to MSE in this case. So I'm going to define a function that takes in a value W and it's squared, right? So that effectively is, people call this a quadratic equation. All right, so I'm going to generate, also to generate a graph, I'm going to generate some data points. Okay, so I'm going to use NumPy linspace from -2 to 2, and I'm going to have 9 steps, right? And I'm going to plot that with this function. So let's go ahead and do that. All right, so that's my data there. And what this is, maybe I'll add a comment here. This represents the loss function. Okay. All right, so I'm gonna run that one, run this one. All right, so now let's go over here. And now I'm going to try to plot this function. Okay, so if you notice, I'm just using matplotlib here, which is also kind of like built in into fastai already. I never declared import matplotlib, right? But I still have it because I'm using it through fastai. I'm plotting the x's on the x-axis, and then on the y-axis, I'm running these data points through this function. Do you guys see that? All right, so I'm going to go ahead and do that. And if you notice, what that gives me is a quadratic function, which has a meaning, right? So I'm going to have an inference function, which is predicting things, the y-pred. And the y-pred is going to be compared to the y-real to calculate the loss, right? That loss is going to be governed by this relationship. Why? Because that is the loss function that we have here. This is going to minimize that error. I should have used probably error here, but anyway. So you can see that there, right? So think of it. So I gave you this example previously, right? I think last Wednesday when you guys asked, I showed you a little graph and I had a little star. Do you guys remember that? That's kind of the same thing I'm doing in a more interactive way. So where do we want? So what does this represent, first of all? This represents here the cost. So we want to minimize that, right? So this function, you can see it's like the laws of the universe that have defined, right? That if you want the best, you have to come down to this point, right? So that you can minimize the loss. Do you see that? But on here, this on the x-axis, that's the thing that governs the difference between the y-pred and the y-real. And that is dependent on the weights, because the weights are multiplied times the input to give you the y-pred. So effectively, that comes here. So when on last week, I gave you like a W here, right? And I said, if you're here, given this function and everything, there's a process, by Jeffrey Hinton and those guys created this or put together the ideas of taking a derivative and figuring out, is this a plus or a minus, so that you know to increment or decrease the weights. Do you guys see that? So that's basically the idea that we're going to try to do now and visualize in a simple example. All right, so I've done that part, okay, define the loss. Now let's go ahead and think a little bit more about this. So I'm going to give you a very simple, super simple example of this. So as you know, the PyTorch framework is basically designed really to do these gradient calculations, right? So I'm going to do this for one value. So let's look at it. So this comes from calculus. Basically, you're getting these derivatives, right? What in the language of machine learning, deep learning, these are called the gradients, basically. In deep learning, gradient usually means the value of a function's derivative at a particular argument value, in this case, the weight. The focus is also, and this is actually really important, when we do this, you do calculus analytically, it's always on the function. You take the function, you take the derivative of the function. But in PyTorch, it's on the variable itself that the emphasis is, or the focus. So this to me is counterintuitive, but this is how it works. So the focus is also on the variable, right? So like this, that's where the derivative is associated, and not the function, e.g. the quadratic, which is counterintuitive. So let's take a look at this, basically. So we define a function here, w squared, right? So this is like saying x squared. So the derivative of x squared should be what? You guys are expert, right? So 2x, right? Way better than me. So you can take that, you take that original function, you take the derivative of it, 2x. But PyTorch does not actually like calculate and give you that function derivative. What it gives you is the value as it goes through that function once you do the derivative of it. You see that? So if I have 3 here, squared, what is that? 9, right? 9. And see, if the derivative of x squared is 2x, then when I run 3 to 2x, it is what? 6, right? 6, right? Yeah. So x squared, and then the derivative of that should be 2x, right? So then if you plug in 3 in there, it's 2 times 3 is 6. Do you see that, guys? That's the basic intuition here. So notice that I'm going to create a variable xt here, right? That's the input to the function. So it's going to go in here. And I have to say in PyTorch that it requires grad. So that's kind of like the thing that we're going to be calculating the derivatives around, right? And so notice then I plug in that 3 into the function and produce yt. Do you see that? So now let's run 3, a tensor, through the function w squared. And let's see what we get. There's your 9. Do you see that? And it's got this grad fn, which basically you're starting to lay out in the PyTorch graph what you want to calculate derivatives for. Everyone with me? Yeah? All right. So now let's take this to the next step in PyTorch itself. I'm going to go ahead. I wrote this very carefully. All right, so let's take a look here. All right, so now we tell PyTorch to calculate the gradients, right? So this was the question you guys kind of had, the update and everything. And if you remember, we have those 3 commands that we always run in the main loop, right? What were they? Clear the gradients, backward, and then step, if you remember, right? So here I'm just doing the backward. Notice that I'm doing it on the yt, which yt is the reference to the f function that takes in the x, and the x is what has the requires grad. Do you guys see that? All right, so let's go ahead and do the backward, and then to view the gradient, we actually need to print xt.grad. Okay. Do you see that? It gives me 6. So in math, the function x squared, if the function is x squared, then the derivative should be 2x. You see that? And so for the variable x equal 3, this is 9, but in the derivative of it, it is 2 times 3, which is 6. Make sense? All right. Any questions so far? Pretty simple. All right. So now, so we've looked at that example. Now let's kind of plot this a little bit more. Now we can also do this for like vectors, right? When you have multiple weights. Now the same gradient scheme, but with 3 weights instead of just 1. So a vector. So we can repeat this exercise. Okay. So again, now we have the tensor, of 3 values here. Let's initialize to 3, 4, and 10. This doesn't matter, right? The initialization could be zeros, random, because these are what? In theory, weights that are going to be updated, right? If they require grad. And so we have these values here. We can print them actually. So down. Okay. So let's go ahead and run that. So you can see 3, 4, and 10. That's a tensor, and it requires grad. Then we have the function here. Okay, so and we want to sum all 3 values in the vector. Okay, so that we can calculate, the optimization basically. So let's go ahead and run that. Now I'm going to run these 2. Okay, so notice I'm invoking the function, same function. I'm running the vectors through it, and I'm going to print yt, and I get one value, 125. Okay? But because this is a function with values where I specified that some of these I want to calculate derivatives for, but remember, you don't actually calculate the function derivative. Instead, you just store the values in the variables themselves. Okay? It's probably for convenience, I would imagine. So now notice that I'm going to run yt backward, which is this one, right? Effectively calculating the derivatives. And then I'm going to print the xt grad. Okay, so 6, 8, 20. What do you guys think about that? X squared, the derivative of x squared is 2x. So if I run 3 to 2x, 6, right? If I run 4 into 2x, 8. If I run 10 into 2x, 20. Do you see that? So that's basically what it's doing. It's it's saving those values. And that's the whole derivatives thing. Do you guys see that? And this is actually the loss function. So this is, if you look at it, that's basically, simplified version of MSE, right? Because it is the quadratic. This is what people love MSE, because you have like one global optima and all that stuff, right? So there's that as well. Any questions so far? Is it making sense? All right, let's take this one step further. All right, let's see what we can take a look at. So now, so we did this. Now let's take a look at plotting this. Where do I have this? Yeah. All right. So I'm going to repeat this same process, but now I'm going to try to repeat it and plot all the weights, basically, so we can see the symbols and everything. Okay. Remember that. Oh, that's why I have this here. Remember that the update rule says what? We use the xt.grad to adjust the weights. Remember that question you guys had, that how do we update the weights, right? So basically we have the weights, and then we say weights equal weights minus, and then the learning rate, which should be like 0.003 or something, and we multiply that times this one, which is what? That is the derivative that we calculated. So effectively, what that should give us is the symbol that we need to modify it, to know if we should be incrementing the weight or subtracting from the weight. Is that clear, guys? So, all right. So we want to visualize this, that sometimes this is going to be negative and sometimes this is going to be positive. Okay. That's what we want to visualize. All right. So I'm going to repeat the exercise here with this code. So we're going to go slowly. All right, so I'm going to copy this one and move this about here. All right, so let's once again, now if you notice, I have added a little bit more. Oh, let me add, like, repeat. Repeat, right? Okay, so now that function that I had before, I modified it a little bit, right? I modified it to be like almost more realistic, and I called it the loss function. What does it take? Y pred and Y real. You guys see that? It takes these values. What do you do with them? You take the difference of Y pred and Y real. It gives you diff, and then you square it basically, right? You guys see that? If you look at this, diff squared is the same as this W squared, which means it has the same shape. That hasn't changed at all. All right? Okay. Then I'm going to create an example here. Okay, so now I'm going to initialize the weights, WT, and I'm also going to have the X input. So remember that for the weight, I need to say requires grad. Why? Because that's the thing that we want derivatives for, because we're going to use that value to update the weights. And I'm just initializing it to like minus 2.5. It doesn't matter because I would be updating this anyway, but it has to start somewhere. For the XT, I just gave it a value 2. And then notice, what is the name of this function? That is the inference function. So that your neural network, whether it's a transformer, a ResNet, linear regression, whatever it is that, right? WX plus B. It starts right there, but it has grown to be a transformer, right? At the end of the day, it's the same thing. So when you do that nn.linear, remember, and then we did nn.linear, nn.linear, and then all of those nn.linears, they're just these, right? We did that example already. All right, but to keep things super simple, I'm even removing the bias, and I'm just doing the XT times WT to predict Y pred, okay? So I can go ahead and do that. All right, so I ran that. Let's add a few more cells in here. This. Okay, so now I'm going to need values for the loss function, right? So I need a y real. So in this case, that's going to be a 1, just for simplicity. So currently this model, 2 times minus 2.5, right? It's going to be what? That's minus 5. Yeah, minus 5. All right, and then I'm going to do, that's the y pred. So the y pred predicts minus 5. We can actually print it. Let me do that. Minus 5, right there. You see that? My inference is predicting a minus 5. I need to train my model to predict what? A 1. Why a 1? Because I'm telling it that I want it to predict a 1. I'm going to print y real here. See that? 1. So this whole mechanism, this is the neural net. The NN is this thing here. Sorry. This is the NN, whether it's NN or CNN or transformer, right? It could be a GPT. It could be chat GPT. Right? It could be anything, right? So that's the inference function, you know, the formula for it, the formulation. Okay. And then we have a minus 5, we have a 1. Now these are going to go into the loss function, which is what I have down here, right? So everyone with me? So I'm going to go in here like that. It's going to take y pred and y real, and then basically it runs it through this function, right, to give you a value. And this is the thing that we're trying to minimize, okay, through our function. So I'm going to go ahead and, did I not run this? There you go. So we have a 36. That's the loss, right? That's it. That's kind of the value that we're getting. This value, 36, what is the interpretation that you should have? That it's somewhere over here or over here. Do you see that? That's basically what it means. That when it runs through that loss thingy, when it runs through this function here, effectively this becomes x squared. So it becomes a quadratic function. So it basically looks like this, which basically means that it's 36, right? 36. 6. All right, so then it's like really high up here. Do you see that? Because it's in relation to the scale that you have on the y-axis. This is the cost or the loss, okay? Your goal is to minimize this. So you can think of the W either being here or here, right? So if the W is here, you want to subtract. If the W is here, you want to add and increment it so that eventually it reaches this one over here. Does that make sense, guys? Any questions? Okay. All right, great. So let's keep going then. So we did that part. Now I'm going to go here. And notice that I can calculate the loss, right? So now this function, right, I can take backward again, right, just like before, backward, right? And that's basically PyTorch telling the computational graph to calculate the gradient. So in this case, WT, which is the one that we defined to be the weights. Do you guys see that? So let's go ahead and do that. Right, and then it gives you, and see there's a sign now there. Do you guys see there's a sign? Okay, so that sign is the trick that's really important because as I wrote it here in the equation, where did I put that? Oh, here, right? This is the update rule that we need to perform. So the grad plugs in there. All right, so what I was thinking about how to view this, usually what you'll do is you'll run this and you'll see it optimized, right? But I tried to print it out here. So let's do that. So now, if you notice, I have a for loop here, and what I'm going to do is I'm going to create a whole bunch of lists of the values. It's like I'm going to give it a W and I take the gradient and print it, right? And also the loss. And there should be a correlation, right? As the loss goes down, it becomes 0 basically, all right? From the values that it has. So I'm going to run this here. I'm going to do W, the line space basically, from -4 to +4. So this should be like the x-axis in this new plot I want to do. So let's do that. Print it out. Oh, lowercase. Okay, those are the values. Now let's just do this in a for loop. So I'm repeating the same exercise, but basically in a for loop. So I can plot it. So let's go ahead. Okay, so let's think a little bit about the logic. I have the same loss function, right? So you can see it's the exact same loss. Again, that loss means the quadratic function. So that's why you always see that. And we saw that it effectively does that. So let me run that. And then here I have these two lists, losses list and grads list. So basically what I'm doing is I'm going to calculate, I'm going to iterate through those values, and I'm going to calculate what the loss is and what the corresponding derivative or gradient was for it, so that we can see the sign change in it. Okay. So I'm going to iterate for item in W, right? So I'm iterating through all these values here. Okay. I'm going to assign that item, right, as a tensor, and then I'm going to say that it requires grad. It becomes the WT. Then I initialize an XT. It just doesn't matter what it is. Now I do the function WT times XT, which becomes YPred. I also have the Y real, right? So it's exactly what I did, but now in a for loop. Once I have my YPred and my Y real, I calculate the loss, right? There's the loss. And then I'm going to, I can print the loss. I'm going to print the loss. But importantly, I'm going to take the loss and append it into a list called losses list. Do you guys see that? Remember that the loss should go down, right? So that's kind of what I'm showing, how the loss behaves in that quadratic function, because I'm going to have the values. So you need to do loss detach, because you need to detach it from the computational graph in PyTorch, and then you convert it to NumPy. That's just like a mechanical thing. Then after that, what do? I'm going to take the loss here, right? And I do backward. What does that do in PyTorch? Calculates the derivatives. So now that I have them, I have basically the associated derivative for that weight, WT, and I'm going to print it, but also add it to the list, grads list. You guys see that? So the goal of this is so I can plot this in relation to each other. So let's go ahead and try this one. All right, and there they are. One thing that should be noticeable already, look at the values of the losses. 81, 49, 25, 9, 1, 1, 9, 25, 49. What did you see with those losses? They were high, they started to go down, and they started to go up again. Do you see that? Does that make sense, guys? What happened to the gradients? Look at them. Minus 36, minus 28, minus 20, minus 12, minus 4, 4, 12, 20, 28. Do you see that? The sign changed. That's very important because that's what's telling you how to update things, okay? So now let's go ahead and plot these. So I've created these lists. So let's go ahead. You can print them out, but I think you guys read through them. You can see them here, actually. All right, so now let's go ahead and print the losses. I'm going to print the losses. So I'm going to do a scatter plot of the W's to the losses, okay? So you can see they have the quadratic shape. And the correlation to the weights should be there as well. Let's see if you catch on to it. So this is W's, right? This is W's, right? This scale to the grads, the derivatives, right? Make sense? So you got the negative values when it's, so think you have to look at both graphs, right? So you have the negative values that tells you, okay, go in one direction, and the positive values that tell you go in another direction. If you look, let's take -3 here, for instance, right? -3. I'm looking for that update rule. Here it is. W, right? -3 times some learning rate, 0.003, right? Effectively minus is plus, so weight plus something, okay? So it's here, go that way. Because you can assume that the W here is like 0.05, add a little bit to it to go in that direction. You guys see that? Towards over there. Let's look at it on the other end. So this is the 0. So let's say now I'm going to grab 2, the positive 2, right? I'm here. So you can see that it correlates to here, right? The minimum is in this direction, so it needs to go that way, right? You guys see that? It needs to go in that direction. Okay, so I'm gonna, let's say 3, so more obvious, right? So 3, so it's here basically, right? Effectively, that's the loss. So I'm gonna go into my function. 3 times 0.003 something, effectively positive, weight minus that. So I'm going to take my weight and decrease it a little bit. Okay. Go in that way. And that's going to take me eventually to the 0 value of the loss. Okay. Any questions? Does this make sense, guys? Any questions, comments, anything you want to? It's a simple example, but hopefully it illustrates kind of how it works. All right, play with this idea. Maybe I think my GPU session died, so I'm gonna have to redo that. But anyway, any questions on this? So basically, what I was, you guys had this question last Wednesday, so I thought about how to do this, and basically this graph, right? So it shows a relationship of the weights after the derivatives to the losses, basically, all governed by MSE, which is actually for regression. You use this as, and it has that quadratic shape. Remember, the function governs the behavior because of this, because of that squared thing. This one. Okay, cross entropy or classification, I showed you as these other things, right? But it's the same idea, right? They just have different shapes because it's a different equation. But you still try to do the same. Anyway, so that's it. Let me see. I believe this session ended. Yeah, less than 1 minute. So that's what happened. I hope it's saved. I'm going to have to start a new session. Give me a second. There we go. All right, so this ended, so I'm going to delete that. Okay. All right, so I need to request a new one. Here we go. All right, so let's start it again. I'm gonna hit desktop. So we were working on fundamentals of computer vision. Okay, so let's see what got saved here. Yeah, everything got saved. Good. All right, so yeah, so let me just rerun this, and then we'll kind of get back to where we were. So I'm gonna click on save. All right, let's hit run. Okay, keep going. All right, so that's kind of where we were. All right. Are there any questions on that idea, that example? No questions? Okay, so now I guess we can continue with our fundamentals of computer vision. We did this as far as here. Okay. So now we have about 20 minutes. So I think what makes sense now, let's try to implement a fast AI. If I'm not hearing any questions about what I was talking about before, we're going to kind of continue with our MNIST data set, right? We did an averaging classifier, a type of a KNN. Now we're going to see how we can use fast AI to build a powerful classifier for the MNIST data set, okay? So let's go ahead and do that, which will be this one here. Okay. So let's start with a very detailed approach. Okay, so this is call it an MNIST fast AI approach. Okay. So let's go ahead and build the data sets first. I'm going to label this as a fast AI. It's actually several versions. Fast AI MNIST classifier. Okay. All right, so I'm going to hit cell here, cell type, markdown, hit run. All right, so we're going to create the data sets first, but it's a similar approach to what we were doing before, right? So we're going to have train X and train Y, right? And then we're going to basically create tuples and list of tuples, basically, of X's and Y's, okay? So you can see here, we have the stacked 3s and the stacked 7s, okay? We're going to concatenate them as a torch tensor. We're going to change the shape to be 28 by 28, okay? So we're going to unspaghettify it to be 28 by 28. That's probably because CNNs actually take images as grids, basically. All right, so we create train X. Then we're going to have the labels as well. And if you notice, we're going to label the 3s as 1s and the 7s as 0s, okay? So this is just, if you notice, because we're concatenate them, all we need to know is the length of the 3s and the length of the 7s. Make sense? Yeah? Okay. All right, and then we create this thing, a list of tuples called dset. We're going to repeat the same exercise for the validation. So we got validation 3s, validation 7s. We concatenate them in a torch tensor. We reshape them, unspaghettify them to be 28 by 28. The labels, once again, All we need to know, because we're concatenating the threes, we need to know the length of the threes, length of the sevens, and then we're just going to have ones and followed by zeros. And those are the labels. Okay. And then we're going to take those and create list of tuples of the x's and the y's, basically. So that effectively, now you know if you ever want to use a fastai learner with your own data, how to create your own data set. Make sense? All right. So let's keep going then. So let's proceed. So I'm going to close this one because I'm done with this Jupyter. Now I'm going to look at this one. All right. Now, once the data is like that, we use data loaders, basically. FastAI data loaders. All right. So I'm going to go ahead. Okay. Here. All right. So I'm going to do a data loader for the D set wrapping, right? So it's just more wrapping. Batch size is going to be 256, and I'm going to call it DL. Then I'm going to use data loader for the validation D set. Batch 256, and I'm going to call it valid DL. And notice then you have data loader, and then you have data loaders, plural. And that just takes DL and valid DL and creates DLS. This is what FastAI wants. So remember, as I said, the trick with these frameworks, I've said this like so many times, right? Figure out what the format of the data should be that it wants, and then everything else will just work through. Okay? Questions? Okay, so let's go ahead. We've created DLS. All right, no errors. Good. Then now you can define your own metrics like an accuracy. You can also define your own loss function there. Okay. You can define your own architecture. Notice that this is just a simple NN linear and then followed by, how many layers does this have? This is an MLP, right? A multi-layer perceptron. Huh? So you can define your own multi-layer perceptron, your own linear, etc. Right? And then we're just going to plug all the values into our learner. Notice this is not a CNN learner or a visual learner. This is just a generic plain vanilla learner of FastAI. Got it? All right. So let's go ahead and do that. So I'm going to grab the define a loss here. All right. So this is going to be MNIST loss. You take predictions and targets. Okay. The predictions, you're going to run them through the sigmoid function here, right? Becomes prediction. And this is a weird way, torchware, but it's a weird way of doing like MSC basically. Just think of it that way. It's a function that's built in PyTorch that works like that. Okay. So like the ones that we've seen before. All right. So run that. So we have one version of a loss function. Then we have a performance metric, accuracy. Okay. So I'm going to do that. Notice that accuracy, you just take what? The reals and the preds, right? And you're going to measure performance. So you got the preds, the corrects, and it's going to measure. This is going to be predicting one neuron, I believe. Yeah. See how it predicts one neuron? And one neuron. If you remember from 520, when we had a binary problem, we could use two neurons or just one. Remember? And if it was a 1, it was one class. If it's a 0, it's the other class. So that's what this is doing. Okay. Obviously, you would have to change your accuracy if it was the different version, the different variation. All right. So let's run this one. Accuracy. Okay. Now that we have all of these, we just need to define the neural network architecture, and that's this here. So you can choose whichever one you want, right? So I'm going to separate them out. So if you want to use a linear model, this is very much like in 520, NN linear, it takes in 28 by 28 and just predicts a 1. No activations, no anything, right? And then we have a simple net using NN sequential. And this takes in the image 28 by 28, runs it through a hidden layer of 30 with an activation of ReLU, and then that linear 30 to 1. Do you guys see that? Any questions on this? This is just, a neural network, like from scratch. So you can do it this way. Notice we've defined the loss basically however you want it with the equations, or you could use the NN functional. You can define the metrics that you want. You can define the architecture that you want, such as a linear or a MLP. This is a MLP. Okay, so let's go ahead. And once you've defined those parameters, you can just plug them into learner and do the learning through that construct. So I'm going to go ahead and see, I have two examples here. So I'm going to copy. Move this one down. Okay, so here, if you wanted to do the linear, right, you invoke learner, you give it DLS, which is the data set, you give it the model, which this example could be the linear model. You're going to say that you want to use stochastic gradient descent, which is a built-in algorithm, right? The loss function that you just defined and the metric for performance. All right, and then all you have to do is learn.fit the number of epochs and the learning rate. Do you guys see that? In the interest of time, I'm only going to do the other one, which will probably be better, right? The MLP. So I'm going to run this one. So remember, this is from fastai, right? So we're using fastai. We've built a DLS. Notice simple net is this one here, the multi-layer perceptron, stochastic gradient descent, the loss, and the accuracy, and the number of epochs will be 40 here with a learning rate of 0.1. Okay, so let's go ahead and do that. There it goes. Pretty fast, right? Power of GPUs. Is the loss going down? 4, 2, yeah, it is going down, right? Okay, great. That's it. I think it finished. All right, so there you go. You just use fastai to train on MNIST and build a binary classifier. Any questions? Because you provided both the train set and the test set, which is validation loss, you actually can have the, both metrics there, the losses, and you can see the accuracy goes up, right? So we arrive at an accuracy of 0.98. Pretty good. Pretty good indeed. Any questions? No questions? All right. Keep going. We have a few minutes left, so all right, we did this. We can compare. It's kind of 98. You can actually plot things. This is with fastai. Okay, so I'm going to go ahead. I'm going to use the PLT matplotlib and learn recorder values, basically, right? So we're going to use that because it's called learn, you see. So I'm invoking learn.object, and I'm passing that fastai. This is actually nice, I would say, from fastai. They're recording everything so you can print out information. So in this case, it's basically printing probably the accuracy. I think it's printing the accuracy. Got it? Yeah. All right. So we did that part. Okay, we're done. Now, kind of wrap up. So we'll finish here. We did a lot there in the previous example, defining our loss function, defining our accuracy metric, etc. But we can actually do it in a more simple way. We can, and also, instead of all that, we can just do, what is it? 4 lines of code. 4 lines of code. All right, even more compressed. As it turns out, Oh, yeah, this is just a comment I'll make later. So one thing that's different here, notice, is I'm going to use an 18-layer model with ResNet, okay? So notice that what I did is, what's been done here is, in this example with fastai, I gave it the model. And what was the model? Just something I defined with classic PyTorch, 520. Not a CNN, right? This is not even deep learning. This is just a multi-layer perceptron. But now I'm going to exchange this. I'm going to take that out, and I'm going to plug in there instead a ResNet. You can see that ResNet 18, which means this is a complex CNN, right? With 18 layers. I don't think any of you have ever built, or maybe some of you have built a CNN of 18 layers, right? That's a lot. David built one of how many layers last semester in 520 for Sci-Fi, I think it was?
Yeah, some of that.
That was
that many.
Yeah, but it was a lot, right? This is 18. And the weights of this, remember, are already set because this is a pre-trained ResNet. So we are doing here, once again, transfer learning, okay? So imagine that it's freezing the last layers and just keeping, or maybe just the last feed forward, or it takes out something and puts in a head. Remember that idea of the head? Same thing. But this time around, it's being done by fastai. So notice also that instead of a classic learner, we have to use a CNN learner. Okay, that's the only little trick. We have our DLS. DLS here, ResNet. The loss function now, it's going to be F cross entropy, and the metrics are accuracy. Okay. Now I notice it says pre-trained false, so I wonder if it's going to train the whole network then if I do this. And if I say true, then it's going to keep some of the weights. We can play with that, but I just noticed that I have false there. All right, so now we have a ResNet in there. We have 0.01 for the learning rate, and we're going to basically do fit for one cycle. Okay, and look at the accuracy, should be about 99%. Okay, so let's go ahead and do that. Okay, so I'm going to invoke the data, CNN learner, ResNet, run. Okay, so it's training. Okay. So this pre-trained false and true, I don't know if any of you have looked up the documentation, but it's interesting because it may be training all the weights of the ResNet. All right, so it gives me 99% accuracy. You can see already, this is, I mean, the other one was pretty good already, but if you have another more so, David, last semester you could have tried this, right, and see what happened. And instead of you built a ResNet, but I think you could have used a ResNet, for instance. All right, so we got 99. I want to try one last thing. I want to change this pre-trained to true because I don't know what it'll say. Intuitively, I want to say here it's keeping some of the weights, and before it just trained the whole thing. But I'll have to check that for sure. $99 still. I'll look up what this means basically. But yeah, that's kind of the class for today. As I said, the goal was to introduce fastai. Okay, we did a lot, I think, and then we'll come back to a few more ideas of the computer vision fundamentals next Wednesday, basically. Any questions? Making sense? All right, so go play with this tool. I'm not going to give you too many homeworks because you guys are working on your RLHF. So I'll end